Disasters occur almost daily worldwide, killing 3 million and adversely affecting 800 million people over the past 20 years. The recent spate of mass casualties plaguing the international burn community showed that situational awareness of on-site medical teams and the off-site hospitals can be quickly overwhelmed. Medical care teams including EMS, burn centers, auxiliary care centers, and public health departments typically function as individual units, but must all work together during mass casualty events. Treatment teams at the scene must monitor an overwhelming number of patients. Transport officers must coordinate transport, and receiving hospitals must prepare for the incoming patients. All these teams often lack sufficient information to most effectively do their job. For years, responders have performed these critical tasks with paper triage tags, clipboards of notes, phones, and handheld radios. This workflow has proven labor-intensive, time-consuming, and prone to human error. The Advanced Health and Disaster Aid Network, called aidn for short, is the only technology of its kind that automates the entire tracking process for providers, vehicles, and patients. A team from the Johns Hopkins University has developed aidn in collaboration with the Burn Center at Washington Hospital, Suburban Hospital, Harvard University Department of Engineering and Applied Sciences, and the University of Virginia Department of Computer Science. aidn is a system of wireless patient sensors, software applications, and mobile computing devices to assist emergency response. To replace paper triage tags, electronic tags were created to continuously monitor patient vital signs and locations, and then communicate this data over an ad hoc wireless mesh network to laptops and PDAs at the scene of the disaster. The electronic triage tag monitors the patient's vital signs, including the heart rate, blood oxygenation level, and EKG. The secret sauce of these electronic triage tags is its wireless ad hoc mesh network. As the patient sensor is turned on, they automatically configure themselves into a wireless mesh network. The endpoint of this mesh network is the patient monitoring station. When a patient sensor is part of the mesh network, it can leapfrog data to each other, and eventually the data will be transferred back to the base station. The monitoring station collects information from all the patient sensors in its mesh network. The mesh network also has self-healing capability, so if any of the patient sensors fail to function, then the rest of the sensors reform a new network configuration based on the remaining sensors. The mesh network is continuously reconfiguring itself to optimize the data transfer capabilities. This technology is key for a disaster or surge capacity scenario, when there's no time to install any communication infrastructure like wireless access points, and the number of patients can increase to an unpredictably large size. The mesh network is critical for these events because it allows a theoretical limit of 65,000 sensors to be on the same network, and its self-healing and self-configuring capability allows for a theoretically limitless range for the span of its wireless coverage. Real-time patient information is gathered by the monitoring station and then instantaneously made available to the distributed response team over the internet. On August 5, 2006, aidn tested its technologies in a mass casualty drill with personnel from Montgomery County Department of Homeland Security. Emergency responders were split into two teams for the disaster drill: a traditional paper-based team equipped with paper triage tags, pens, forms, charts, and whiteboards, and the electronic team equipped with aidn technologies, wireless automated sensors or e-tags, field PDAs, scanners, laptops, and web portals. Just prior to the drill, the electronic team of responders was trained for 10 minutes on the specific technology they were going to use. The incident commander was trained to use the disaster information dashboard. The triage officer and triage team were trained to use the electronic triage tags and PDAs. The treatment officer was trained to use the patient monitoring dashboard. The training time was limited to just 10 minutes to simulate the time pressures of real-world disasters, where responders would arrive from multiple jurisdictions and there would be little time for training prior to deployment. The drill began with a simulated bus accident involving 20 passengers. This is not an unlikely situation at Montgomery Blair High School, where the incident was staged. The high school contains the intersections of the Washington, D.C. Capitol Beltway and a notoriously busy 6-lane road. The volunteers that were playing the role of the patients got on the bus and they were given their various roles and elements. The medical personnel then responded to the call. The patients still on the bus were triaged and the injuries were assessed by each medical team. Here the patients were tagged with either the customary paper tags or the electronic aidn tags. As each electronic tag was turned on, the tag self-configured into an ad hoc wireless network. No prior installation of communication infrastructure was necessary. As soon as each electronic tag was turned on, they began to immediately transfer data to the monitoring station. The teams then separated their patients into the standard triage categories of green, yellow, and red, denoting how dire each patient's individual need for treatment was. Once categorized, the two teams moved their patients to a treatment area. One treatment area was set up for the paper and pen team, and another for the electronic team. The treatment officer, triage officer, transport officer, and medical staff at the hospital can monitor each patient as needed on their laptops well before they would normally be able to. This information is supplemented with additional patient data, such as patient photos, chief complaints, injuries, medications, and allergies, which were acquired and recorded by the PDAs and license scanners used by the medical team in the field. All this automatic information transfer allowed every facet of the electronic team to be armed with information. Patients were held at the scene for 22 minutes prior to transport to either a hospital or a temporary treatment center. In those 22 minutes, vital signs were reliably captured by the e-tags and reported over the ad hoc network. Vital sign readings for each patient were reported in real time and archived into a database for the electronic team. A high-risk patient was identified to need an additional level of monitoring beyond the pulse oximeter, so a wireless EKG sensor was quickly applied to him. This access to critical information at the earliest stages of development may mean the difference between life and death for a patient. From the incident scene, the patients were then transported via ambulance to either the treatment center stage in the local high school or suburban hospital. In transport, the electronic team sent specific information about arriving patients and estimated arrival times directly to the receiving hospital. At the treatment center, cots were laid out for the patients, and the monitoring stations were effortlessly mobilized as needed, being moved from the disaster site to the treatment center and seamlessly continuing patient monitoring. This allowed for all patients to receive their final treatment in a timely fashion. Although the electronic team received only 10 minutes of training on how to use the e-tags, they were still able to triage all patients at a comparable speed as the paper team. Time for responders to triage all 10 patients and report the triage information to the incident commander was 8 minutes 40 seconds in the electronic group and 9 minutes in the paper group. The electronic team was able to access and triage the patients approximately 3 times as frequently as the paper team. This enabled a smaller number of medics to assist more patients. Suburban hospital, public health, and a temporary treatment center accessed real-time data of the patients in the electronic team prior to the arrival of the patients at the care facility, thus providing important information to medical personnel and lowering the burden of communication. In this drill, automated monitoring more than doubled the patient care capacity of field responders. This technology is poised to make a similarly profound impact on our nation's hospitals. The aidn system can be easily adapted to perform all the tasks of modern medical monitoring devices while taking a patient-centric approach. Medical personnel would only need to learn a single interface that could perform numerous tasks for each patient as needed. In time, the current aidn system has the potential to automate the monitoring in modern hospitals while allowing medical staff to monitor more patients more effectively.